Today's talk is titled How to Make People Immortal and Why It's Not a Good Idea. Just having a quick look on the abstract. This is a very interesting talk. And I hope everybody gets enlightened by these ideas. Professor?
Thank you. So very happy to be talking about this. So this is the title of my talk, and these are some of my other engagements. And I'm going to be, and this is work that is joined with these people listed here: Jonathan Stern, Julian Higgins, Ian Schreier, and Sonia Hernandez-Diaz, in case that you want to learn more about what I'm going to be discussing. Okay, so the main issue here is that so we've been talking a lot about AI during this conference and in general over the last few years, and sometimes not only the hype, which there is a lot, but also the actual talks about AI don't make explicit something that I think is obvious to all of you, that is that AI is a sophisticated form of data analysis. It's not in 2025, AI is not an intelligent, sentient machine. It's something that we do with data. And we have now new tools that do things that we couldn't do before, and we call them AI. So in health, the analysis of data for decades had been based on large healthcare databases like electronic health records or insurance claims or biobanks, etc. And this is what a mixture of statisticians and computer scientists and epidemiologists have been doing for a very long time. They take massive amounts of data that are generated during routine healthcare and use that data to infer which medical interventions are most effective, safest, etc. Okay, so it turns out that a lot of these analyses are fundamentally flawed. And I'm going to give you an examples for a very surprising reason. If we're talking about AI, before even we start talking about that, we need to make sure that this reason doesn't happen. So let me explain what this reason is. This is something that is known in the literature as immortal time. This is a time during which a person cannot die. If we do our analysis in such a way that is impossible, we make it impossible for a person to die during a certain interval, then we say that that person is immortal during that time. We say there is immortal time. And of course, if we design our analysis of data in such a way that there is immortal time, we will have a bias. We will have a big problem. There is nothing in all the conversations we discussed about, all the conversations that we had about AI there's nothing that prevents this from happening again. Because if an AI system is learning from what humans do, well, this is what humans do all the time. So let me explain the concept of immortal time so you can see it. And I'm going to do this with the earliest example of immortal time that I've been able to find in the literature. This is by Farr, who was working in London in the 1850s, and he recognized this problem in data analysis for the first time in a very simple case, which it was essentially he was looking at the average age at death of different groups. And he found that soldiers, on average, die at 22 years. But captains, on average, die at 37 years. And generals, on average, die after age 50. And he joked about this and say, okay, well, maybe we should make all our soldiers generals so they live longer, right? You can see what the problem is here. This happens with priests and bishops too. Bishops tend to die later ages than priests. Of course, because they have to survive until they become bishops. In this case, they have to survive until they become generals. So this is obvious. I'm sure everyone in this room sees the problem, say, well, what, are you really going to give a talk about this? How is this possibly an important thing? Well, it turns out that this happens over and over and over in analysis of data. Another example, a very famous paper that found that Oscar winners live longer than non-Oscar winners. And again, this leads to a very convoluted discussion about how winning an Oscar makes you happier in some way, so you live longer, etc., etc. You see the problem, it's exactly the same problem. Now, with the soldiers and the generals, it was obvious. With this, it's also obvious, but not obvious enough that went through all the process to get published in one of the most prominent medical journals in the world. So this happens over and over and over, and it's there, and we don't see it. So this is another example of immortal time. Now, in medical research, the first dangerous example of this was in the late 1960s, early 1970s, when heart transplants were done for the first time. So there were a couple of very prominent studies that were published in the Lancet and Annals of Internal Medicine, two very top journals in this. And these studies found that people who got a heart transplant live longer than people who didn't get a heart transplant. You say, well, yeah, that's a very good study, right? You compare people who get a heart transplant, people who don't get a heart transplant. And isn't that what you want to do? Well, not really, because these are people who are candidates for heart transplant. They're waiting for a heart transplant, okay? And then some of them, by chance, because someone had a motorcycle accident and is killed, and that person happens to be compatible with you, then you get a heart transplant. That's by chance. So people who got a heart transplant are people who have already been on the wait list for some time until they get a heart transplant. Whereas people who don't get a heart transplant may have just joined the wait list for heart transplants. It's like the soldiers and the generals again. So of course, if you start counting from the time that you join the wait list, people who get a heart transplant have already lived for some time before they get to the point where they get the heart transplant. So that's a case of immortal time. So you're starting to see now how this becomes more subtle now. From the soldiers and generals, which is of course, to now heart transplant versus no heart transplant, it's the same problem. But this keeps happening all the time. And then if you look at the literature, at the medical literature in the last 30 or 40 years, or even last week, there are a lot of studies in which you find, for example, that corticosteroids are associated with 30% lower mortality, beta blockers 60% lower mortality, statins 70% lower risk of cancer. All these things are crazy. It's not possible. I mean, we wish that these things were true, but they cannot possibly be true. These are all examples of immortal time. And this is one of the most prevalent problems that we find in the medical literature. And I'm going to talk for the next few minutes about why this happens and how we can prevent it from happening. And this is one of the most basic building blocks for a working AI. If we want to have AI that analyzes data well, this has to be fixed, and it's not being fixed right now. This keeps happening, even in very sophisticated data analysis, because people are thinking of the data they have in front of them and how they say, well, heart transplant or no heart transplant, right? Isn't that the question? No, that is not the question. So let's talk about this a little bit more. Because as I said, this is a problem that has been known for a very long time. And it should not happen. This is a problem that should not happen. Because we know how to fix it. I mean, far in the 19th century, we was talking about this, but after the heart transplant studies were published, Miguel, who was a statistician at NIH, quickly identified the problem and started to talk about how to eliminate it. Okay, so let's talk about this. The way I will discuss this is about giving you a unified framework for causal inference from data. So this is applicable to any type of data analysis, including AI-based analysis that we do with large databases. And I'm going to describe two different types of immortal time. One happens because of an incorrect selection of subjects in the study, and the other one happens because of misclassification of a treatment group. The unifying framework is the target trial. The target trial is some hypothetical randomized experiment that didn't happen, but we try to emulate with the data that we have. And this is essentially what causal inference from observational data is. It's some attempt to emulate a target trial. So the question is not whether we are trying to emulate a target trial, is whether we make that target trial explicit or not. We're always doing that. That is what causal inference is. But that has not always been an explicit thing, even though there is a literature over time over that does that. So if you think about causal inference, it has two steps, right? It's a very simple process in the sense that the first step is to ask a causal question, and the second step is to answer the causal question. This is probably the most important slide that I'm going to show today, because if we skip the first one, we don't ask a causal question explicitly. We say things like, well, I want to know what is the effect of heart transplant, and that's it. You don't talk about what is actually the randomized experiment that you are trying to emulate. Then things like immortal time happen. So the most important thing is first, be very explicit about the target trial, about what is the experiment that we are trying to emulate. And then if we conduct the experiment. If we can't, then we will emulate it using observational data in an explicit way. So when I say that we have to be explicit about the experiment, it means we need to be able to describe the components of a protocol of a target trial, which are the same components of any other experiment. We need to know who are the people who are being eligible, the treatment strategies that we're going to assign them, how we're going to assign them to treatment, the outcomes of interest when the follow-up starts and when it ends, and then of course the causal contrast, intention to treat effect or per-protocol effect, and the analysis and the assumptions. So these are, and once we know the question, then we go to the healthcare databases and map each of the components of a target trial, the protocol of a target trial, with the data that we actually have. And that is how this works. Again, it doesn't matter whether we are doing this with a 2x2 table, with a logistic model, with neural networks, deep learning. Any method that we are using will be based on this framework, or will have problems like immortal time. Okay, so by being very explicit about this process of the emulation of a target trial, we don't eliminate all possible biases, because if there are data constraints, some of the important variables that we need to adjust for are not in the data, or there is measurement error in the data. That is not solved by following this process of specification and emulation of a target trial. But the biases that are due to an incorrect design of the analysis, those biases disappear. And one of those biases is immortal time. All right, so let's talk about immortal time. First, there is a type of immortal time that happens when the selection of the individuals into the analysis is based on things that happen after the start of follow-up. Okay, so let me give you an example. Let's say that we have a randomized trial with 16 million people, just huge, because I don't want to worry about p-values or confidence intervals here. We have a randomized trial, say, with 8 million people in each arm. And of the 8 million people that are assigned to treatment, let's call them Z equals one arm, 2 million died in the first 3 months, 4 million died between month 4 and 10. Of the 8 million people assigned to no treatment, Z equals 0, 1 million died in the first 3 months and 2 million in months 4 to 12. Well, this would be the survivor curves that we will find there. There are more people dying in those exposed to this treatment than in people who don't take the treatment, and that is how we would do it. We could compute the risk in each group, which is about a half at 12 months, and there is 6/8 in the treated, 3/8 in the untreated. So the risk ratio is 2, twice as likely to die if you are exposed to this treatment that you are not exposed. This is a very simple way of analyzing data from a trial. Now let's say that in these randomized trials, investigators accidentally deleted the first 3 months of follow-up. Or the first 3, they just lost the data. So for each person in the trial, they only have data after 3 months of follow-up. Okay, now that is a problem, and they have to decide what to do. One thing that they could do is say, okay, we are going to continue our analysis as if nothing happened, and the other thing is, well, we are going to start the curves at 3 months rather than 0 months because we have lost the data. So if they do the first thing, they say, okay, we are going to continue as if nothing had happened because they have lost data on the first 3 months of follow-up. They have lost data on everyone who dies in the first 3 months of follow-up. They don't have them. So it's going to look like no one dies in the first 3 months of follow-up. That's immortal time. If they start, and therefore the survivor curves that they're getting are wrong. They're not the ones from the trial with the full data. If they decide, well, let's start at 3 months, right, at 2 months, well, they're going to move this red line there and to 0 and this there. So it's going to look something like this. That's also going to be wrong. There is no solution. If you lose the data, there is nothing that you can do because the assignment to treatment and the eligibility are not aligned. We are putting people into the analysis based on something that happens after the start of follow-up. That creates a bias. Okay, so this form of selection bias, because we are selecting people based on things that happen after the start of follow-up, is one of the sources of immortal time that we can have, and there is no way to fix it. We don't have the data. There is nothing that we can do here unless we make heroic assumptions. And we can show this for those of you who are into causal graphs by showing the causal graph, how this is due to conditioning on a collider, which is the survival after three months. Now, of course, this is not going to happen. There are no trials where people delete by accident the first 3 months of follow-up. But you see what the problem is. Because now we move into healthcare databases. And let's say that we have, again, 16 million people, 8 of them start treatment, and then at time 0, and 8 million do not start treatment at time 0, and the number of deaths is the same as before. So if we had data from a healthcare database that looks like this, we could do the same analysis as in the trial, maybe with further adjustment for confounders if needed. But the point is that we analyze the observational data essentially in the same way as we analyze the data from a randomized trial. And this is where the problem can happen, because now let's say that the people who are doing this analysis decide to restrict it to those who have survived the first 3 months of follow-up. And this is justified in practice for many reasons. So I only want people who have survived for some time. I only want people who have a minimum amount of data. I only want people, etc. But the result of restricting the analysis to people who have survived for 3 months, to say people who have a second visit during the follow-up, there are many ways in which this is. It's the same as deleting the data from the first 3 months. And we just saw that if we delete the data from the first 3 months in an actual randomized experiment, we have bias that cannot be fixed. And that's the same thing that happens in many analyses of observational data. So if we were working with AI, and one of the criteria that we are using is having people who have at least 3 months of follow-up in the data, so they have enough data, okay, we have bias now. And this doesn't matter which analysis method we are using. Again, this could be a deep learning model with 1 billion parameters, or 1 trillion, it doesn't matter. It's going to create the same bias. Okay, which is this, what I showed you before. So this is known as prevalent user bias in many cases, and this is responsible for some of the most catastrophic failures of causal inference that we have seen in the medical literature in the last few decades, like the case of hormone therapy and coronary heart disease, that everybody thought, based on analysis of healthcare databases, that hormone therapy lowered the risk of heart disease. Lots of women were given hormone therapy, thousands died or had heart disease, and only 20 years later, with a randomized trial, we learned that that was wrong. It was this problem. So I'm not talking about an academic problem. This is something that affects people's lives. And this happens also often in studies, like, let's say that we are trying to estimate, say, the effect of vaccination during pregnancy on risk of abortion. And let's say that women are vaccinated with their first visit, their first prenatal visit, that happens around 10 weeks. But we restrict our analysis to women who have a second visit, which happens 4 weeks later, while still pregnant. Well, the risk of abortion then between 10 weeks and 14 weeks is going to be 0. But it's not true. It's just how we ask the question. The question is not asked in the right way. So the analysis cannot help there. Now, and you could say, but we will see that the survival curves are flat, and therefore we see what the problem is. The problem is that the interval of immortal time is not the same for every person. So the survival curves are not flat. You don't see that. And also, many analyses don't even show the survival curves because they only look at the hazard ratio, and therefore there is no way of finding it. So, so this means that we always need to ask our question to specify our target trial in such a way that the start of follow-up is when people are eligible and people start the treatment. It has to be the assignment to treatment and the eligibility for the study need to be synchronized at time 0. Okay, that was one type of immortal time. The other type of immortal time is due to misclassification, and this happens when people are classified into a treatment group based on what they do in the future. And you say, why? I mean, we will never do that in a trial. Right, we will never do that in a trial, but we do that sometimes in observational analysis when we don't have randomization, because it's hard to assign people to one group or the other at the start of follow-up. So, I mean, this happens. This doesn't happen when we are talking about the effect of a point treatment, a treatment that is either you are treated or you are not treated at baseline doesn't happen. It happens when we're talking about the effect of a treatment strategy that is sustained over the follow-up, which is most of the questions that we are actually about things that happen over a period of time. We don't talk about the effect of when we refer to the effect of aspirin. We don't mean the effect of taking one aspirin at baseline. We are talking about the effect of taking aspirin during the follow-up. So that's a treatment strategy that is sustained during the follow-up. And some of these treatment strategies have something that they are not distinguishable at time zero. And I'm going to explain what this means, because this is the core of the problem. We don't know at time zero who is going to be a general in the future and who is not going to be a general in the future. That's really the problem when we're looking at the soldiers. So let's say that we have a randomized trial that, like the one that I described before. In this trial, let's say that the investigators lose access to the variable that indicates which treatment people were assigned to, the Z variable that I gave you before. Okay, if they lose access to that variable, they delete it by mistake, but they can see the treatment that people actually took. That's not a very big problem, because if they say that someone takes treatment, that means that that person was assigned to treatment, didn't take treatment, was assigned to no treatment. So they can reconstruct the assignment based on the actual treatment that people took. But now let's say that we have a randomized trial with different treatment strategies that are, first, start treatment within 3 months, not immediately at baseline, but within 3 months, or do not start treatment ever. Now, if they lose the variable that indicates the assignment, if we look at baseline, and there is a person who doesn't take treatment at baseline, now we don't know whether that person was assigned to start treatment within 3 months or to not start in treatment, because that person could be assigned to start treatment within 3 months, but at time zero, at month zero, that person is still not starting treatment. So these two treatment strategies are not distinguishable at the baseline, looking at the data on treatment that the person had. This is the core of this. So this is really what causes the immortal time. That many of the comparisons that we make are about this type of strategies. Think of a heart transplant. At time zero, when you join the wait list, we still don't know if you are going to get a heart transplant or not. So how do we classify people into one group or the other at time zero without looking into the future? When we look into the future is when we have the problem. That is really a thing. So let's say that we have data from this randomized trial in which 8 million people were assigned to start treatment within 3 months. These red lines are people, and the dots are deaths. So in the group assigned treatment within 3 months, they were assigned at time zero, but before they started treatment at 3 months, let's say, just to keep it simple, that everyone started at exactly 3 months, 2 people died. Okay? These people died before they started treatment, but they were assigned to start treatment within 3 months. Whereas here, in this group, we see that no one started treatment, and also 2 people died in the first 3 months. If this is a randomized trial, we know that these 2 deaths go into the treated group, and these 2 deaths go into the untreated group, because we know the assignment. So this is what happens if you assign people to start treatment within 3 months. This is what happens if you assign treatment to never start in treatment. But and in this case, there is no difference in the risk of death between both groups in this example that I gave you. Now, if the investigator had deleted the indicator Z, they don't know who is in the red group or in the black group. Now there is a problem, because when they look at these 2 people, they see that they die before starting treatment, so they don't know if they're in this group or in this group. So without that information on assignment, it's hard to decide. We don't know. They could be in either group. If we just take those 2 people and put them in the no treatment group, now we have a problem, because now all the deaths are counting in the no treatment group. That's the immortal time. We're making everyone in the treatment group now immortal for 3 months. It's not correct, but it's what we do if we don't have information on assignment. And that is exactly what happens in the analysis of healthcare databases. We don't have information on assignment. We just see what people do. But we don't have someone telling us what was inside the mind of a doctor who decided what to do that. We don't have it. AI, it doesn't have it. So this is definitely what we don't want to do, because this is putting all the generals, all the soldiers who were going to be generals but died before there, we are putting them there. Okay, all the priests who were going to be bishops but they died. All the actors who were going to be Oscar winners but they died, we are moving in there. All the people who were going to get a heart transplant, we're moving. That's the same problem over and over and over. It has happened since humans started doing data analysis for causal inference. So something that we could do, I mean, this is the equivalent of changing the assignment variable by a new one, let's call it Z star, which is, say, you are going to be assigned to the treatment group if you were treated, essentially, at some point during the follow-up. We're looking into the future. Okay, so that's the immortal time, and that creates bias, because now the treated group is going to be great. It's going to look great, because, of course, we're getting rid of all those early deaths there. And that is a bias that can be represented as a misclassification bias. All right. Now, something that people have done is to say, well, let's move all this time, not only the deaths, but all the deaths and the non-deaths to the untreated group and keep the treated started at 3 months. Okay, that solves some of the problem. It creates other problems, because now we are not able to estimate the survivor curves at time 0 in both groups, because now these are started at time 3, and there is a selection by that time, so these people are not comparable with that. This is going to eliminate the gross form of the bias, but it doesn't solve the whole problem, and that is what happens when people use hazard ratios. That's a very common way of analyzing health data, but it doesn't give you absolute risks from time 0, so it's not ideal for decision making. Another thing that we can do is to change the question. We can change the question, say, rather than asking the question of what happens from time 0, let's ask what happens from time 3. That is a valid question. It's a different question that sometimes is also very helpful. For example, when we were estimating the effects of the COVID vaccines during the pandemic, this is what we did. Rather than estimating the effect of being assigned an appointment for a vaccine at time 0, we said, okay, we're going to estimate the effect of actually receiving the vaccine. But that requires that we have to move time 0 from all these people to that point. If we don't do it, we will get bias. Again, if we think of what the target trial is, this is a different question. We can do this without a problem. If we don't want to change the causal question, then the situation is a little bit more complicated, because if we don't want to change the causal question, then we have to either use the G formula, which is the most general form of causal inference. This is something that was developed by Jamie Robbins in the late 80s, and that computer scientists have then rediscovered a couple of times, and it's at the basis of all methods for causal inference. Now we are combining that with deep learning and AI, or you have to use cloning, censoring, and weighting, which is a different method. I don't really have time to go into here now. But the point here is that this immortal time that happens so often. I mean, I can assure you, you open the best medical journal of the last week, and in the top 5, there will be at least one paper that has this problem to some extent. It's extremely common. Now, it happens either because of selection bias, because of misclassification bias, as I said, and we know how to eliminate this problem. The problem happens because there is a alignment of the eligibility criteria and the treatment assignment in the hypothetical randomized trial we are trying to emulate, the target trial. So to solve the problem, the first thing we have to do is to be explicit about what the target trial is. And once we do that, then the bias will disappear, because immortal time doesn't exist in randomized trials. It only exists in observational emulations of randomized trials that do not are not explicit about the question that we're trying to answer. The question is never being treated versus not being treated. Taking having a heart transplant versus not having heart transplant. A lot of the problems that we're finding with the failures of AI to answer questions in the correct way is not because of data limitations. It's not because deep learning is not great at finding patterns in the data. It's because the question itself is not being asked in the correct way. And we make people immortal, which, as I said at the start, is not a good idea. So thank you, and I'm going to finish here.
Thank you, Doctor, for the nice talk. We can open the floor for questions.
Thank you. I'm Kun Nguyen from G42, and I have one question. Do you think that the machine learning paradigm like strand stat split, like for example, because this is like a follow-up study, so we can split the data based on time and use the earlier data to estimate the causal effect, and then you can check if that kind of generalize into the validation data? Is it kind of like detection if you have some like bad estimation? Yeah, what do you think?
Well, as I said, if by machine learning you mean some form, say, of deep neural networks or something like that, that is at the core, that's a method to find patterns. Okay, it's like rather than fitting a linear regression model, which is also a method to find patterns, but very, very constrained, and maybe with 50 parameters, maybe 100 parameters. Now we can do that in a much more complex data set with 1 billion parameters, much better at finding patterns. But that, it doesn't matter how good your pattern recognition is. If the question is not set up in the right way, then this is not going to help, because we are still going to be using data from treatment groups that are not comparable, period. And it doesn't matter how we compare them. That is one of the messages here. If you know what your target trial is, if you know what if you haven't defined I mean, not you, I'm saying just in general, but if you haven't defined your eligibility criteria, your treatment assignment, how people go into each group, that is 90% of the problem. And then in some of these cases, machine learning can help with the other 10%.
We can have the last question.
Okay. Thanks, Professor. Can we have, or does AI currently have the capacity to fix the question? That's okay.
So now we're talking about a different form of AI, in the sense, because when we talk about AI, when people talk about AI, and we saw it in the talks, people are talking about different things. Some people are talking about deep learning, period. Some people are talking about deep learning combined with reinforcement learning or something. Some people are talking about reinforcement and deep learning plus reinforcement learning with human subject feedback, or some people are talking about that combined with some rules or the physical laws. Here, if you are talking about AI by saying, okay, can we use AI, meaning in terms of a language model, deep learning with reinforcement learning with human feedback, we could use that to guide the investigator asking the questions. In that case, yes.
We can have one last.
Thanks for the presentation. One quick question regarding synthetic data. nowadays a lot of experiments are happening by synthetic data. So you're using AI to create samples and for all this to make sure the response rate is biased. Or so what is your thoughts on that? I know it's not a good practice, but what is your thoughts on synthetic data?
So to create synthetic data that is valid for causal inference, we need to know the true data generating process. So it's the same thing. Think of games, okay? We have AI systems that play games better than any human. Think of Go, right? Why? Because we can generate data. We can play an arbitrarily large number of experiments or games, and then we can use reinforcement learning in a clever way. But we can do that because we know the rules of the game. We know how the data can be generated in a valid way. For healthcare data, we don't know the rules of the game. So we can try to generate data under assumptions about how we believe that the world works. If our assumptions are correct, the synthetic data will be correct. But we don't have guarantee that it will be correct because we don't know the rules of the game.
Thank you.
Sure.
We have the last
Thank you.
question.
Oh, guess I'm lucky. Well, say you come up with this study that avoids immortal time, like basically the whole px equals to 1 issue. And you have the study that's free of that sort of bias. But you want to compare it to other studies within the same domain. You say, like nearly all studies or many studies do have this sort of bias inherent to them. How exactly do you make that comparison?
The comparisons across studies? You mean?
Right. All of the other studies may have that bias within them, but this one, let's say you've eliminated that bias. How exactly do you figure that out?
I mean, we try to convince the people who did the other studies to do it right.
Thank you, Professor Miguel. The talk very interesting. Have a round of applause.